Good afternoon to everybody. So we open now the afternoon session, and the first speaker is Archil Kobakhidze, and he will talk about gravitational instanton, the strong CP problem, and its companion, axion solution. So please.
Thank you, Alessandra, and let me join everyone thanking organizers for putting up a very engaging and interesting program, and for inviting me to talk about this stuff. This is work-based. We started this work a few years ago, and it's based on this significant contribution from my students and collaborators at the University of Sydney. Yeah, I'll be talking about gravitational instantons and their hopefully some new things about the influence of gravitational instantons on strong CP problem and its axion solution. So more generally, so when we started this looking at the gravitational instantons, the question more general that are there any reliably and robustly estimated quantum gravitational effects which are also phenomenologically relevant in terms of particle physics, of course. Of course, we know that the inflation presumably is the case in this partially, but we want to talk about more on this non-cosmological setting. And of course, this is not the first. We are not the first, of course, asking this question. There are some quite relevant previous works by various authors. There are a few works cited in this slide, and more recently, valiant collaborators who are looking at various aspects of gravity and the gravitational instanton, quantum gravity, let's say the neutrino mass generation and other stuff. Okay, so of course, if you ask the question, and if you're concerned only about the local interactions, the local gravitational interactions, the answer is presumably no, because to have any feasible quantum gravity effects, you need to resolve the scales of order of a Planck scale, which is not feasible in any foreseeable experiment. But we know that the physics is not just defined by the local interactions, but defined by the ground structure of the theory. And that's where we may have some interesting effects in related long-range correlations, which then induce some local operators in the effective field theory. So the good example of this is, of course, strong CP problem and the theta and the associated theta phase, which comes these operators which violate CP in the standard model. Of course, this in principle, you can write the operators for gluons and for QED, but we know that the QED, at least if we're concerned about the flat space-time, no gravity, this term it can be removed as a total derivative term. But another term, of course, gives physical effects, which is known through various CP violating decays of mesons, and most prominently through the calculation of electric dipole moment of neutron. And we know that this parameter has to be severely constrained. And that constitutes the strong CP problem. Okay. So another place where those, of course, related, where these operators come into place is through the anomalies. Quantum anomalies. We know that the divergence of axial currents contains these two terms. And again, I mean, if you ask the question whether there are processes which do not conserve the axial charge, the answer is yes, but this is entirely comes from the UCD sector. And again, this is all related with the topology and non-trivial Chern-Podryagin index in the case of non-abelian gauge theories. And again, this is a very well-known thing that this is all related to the so-called Arya-Zinger index theorem of the elliptic operators, the Dirac operator in particular, and of course the change in the axial charge is given by the difference between the zero modes, left and right, and the zero modes of fermionic particles. Now, specific realization we know it's so famous PPST instantons, where the topological charge is equal to 1. So, of course, this is all very well known. Which is I want to bring this again your attention because it will be relevant for what we're talking about regarding the gravitational instantons. We know that these interactions are the amplitude of amplitude mediated by the instantons is in the semi-classical level is suppressed by this famous factor. But on the other hand, this is at least qualitatively important for the other understanding why the eta prime mass is much bigger than pion mass and so on. So it has ramification, phenomenological ramifications. Now, again, coming back to the axions, of course, one of the most elegant solutions, presumably, of the strong CP problem is the axion where we promote the phase to and introduce pseudoscalar field, which presumably comes from the spontaneous symmetry breaking of axial symmetry, known as the Pechakian symmetry. And in dilute gas approximation, you can compute the potential to show that the axion relaxes in the minimum where it cancels out this theta contribution completely. So this is a very elegant solution, dynamical solution to the strong CP problem. On top of that, of course, we have the prediction for a very light pseudoscalar particle, which, of course, is a very good candidate for the dark matter. And this is the phenomenological interest and various experimental efforts to find this particle is very well known and discussed during this workshop, of course. All right. Now, I want to go back now to the anomalies and remind you that the axial anomaly, in the case when we include the gravity, contains another contribution from the terms which are similar to Young-Mills structure, but now with the Riemann curvature and its dual. And diagrammatically, the diagram is very similar to the Young-Mills case. It's just that the external fields here now, not the gauge fields, but the gravitons. And the question is that, are there any instanton interpretation of this anomaly at all? Okay, because we know that we have the contribution to the one axial anomaly from the QED, but there are no instantons, so it's kind of irrelevant to what we are talking about. Now, let me go through the instantons, the gravitational instantons in some generality first, and then I will present the specific gravitational instantons where I think that it has a relevance to the strong CP problem. Now, in quantum gravity theory, we can imitate instanton effects by summing over the all possible manifolds with arbitrary topology in Euclidean path integral formulation of quantum gravity. And we know that we immediately will have a problem with that. So unlike Young-Mills theory, in gravitational actions are not positive definite in general. However, if we concern only with the manifolds which are asymptotically Euclidean, then there is this very powerful positive action theorem, which tells us that all Ricci flat vacuum manifolds has the positive action. So we can have at least the interpretation of the instantons in semi-classical level. The interesting thing about this is that, though, that if we consider exactly Euclidean, space-time, flat space-time at the boundary, then this saturated S equal to 0, the actions that is saturated, the limit is saturated only by the flat space-time solution. So if the asymptotics are just the usual flat globally and locally flat Euclidean manifolds, then there are no instantons. In fact, that's what the theorem tells you. And another thing is that it turns out that you can have a zero action solution if you assume that the manifold is somehow twisted at the boundaries and it's actually locally Euclidean, so other spaces. So this is good news in principle. So you can have self-dual and anti-self-dual gravitational solutions, and it's saturated with bound s equal to 0. You may think that that the quantum gravity effects related to this type of instantons are quite significant, or at least on the border of applicability with the semi-classical approximation. However, the things are not that simple. If you very carefully go and look at the Dirac index theorem for those instantons, you can quickly find out that there is no zero modes associated with this type of instantons, and therefore they are irrelevant to the violation of the chiral number. Okay. So let me give you before I go and consider more complicated solutions and include the gauge fields, let me give you an example, the very simple example of these instanton solutions. This is a metric known as the Iguchi-Hansen metric, which describes self-dual, anti-self-dual solution. In this case, in a metric form, and you can see that it contains like a usual Young-Mills instanton, the parameter A, which measures actually, which is arbitrary length parameter in the classical limit. And in the limit A going to 0, we'll have a flat space-time solution. And finally, of course, this contains so-called coordinate singularity. So it contains a horizon like a black hole in a certain sense. Now, this is a geometric form, near horizon limited geometry looks like a plane. And one of the things about this, if we want this geometry to be geodesically complete, we have to restrict one of the angular variables, which now goes from 0 and 2 pi rather than 0 from 4 pi. Now, what does that mean? That we are effectively halving the space, taking then, at infinity the points and antipodally identifying them. Okay, so that's a space. Again, it's not globally flat at the boundaries, but it's locally flat. Now, of course, this topology of this P3 is non-trivial, given by the integers, and so this kind of describes the analog of Young-Mills instantons. However, you can compute the action indeed and confirm that it's 0 according to the positive action theorem. And you can also compute that the index of the Dirac operator is 0 as well. So these particular instantons by itself have no relevance to the chiral symmetry breaking, anomalous chiral symmetry breaking. However, what is interesting is that now let us try to include gauge fields and look at the hybrid configurations. And it turns out that even for the electromagnetism, we have the non-trivial instanton solutions on these backgrounds. So this is quite unexpected. What it means that in principle, we have in the standard model new sources of CP violation, which are associated with the topological terms of the hypercharge and the AC2. And another interesting thing about this is that if we assume, the completeness of the space-time, which in other words saying is that we assume that we can define the fermions on the space-time, then we, by bonus, getting the charge quantization condition for these theories. So I want to now consider non-abelian gauge theories and so-called colored Iguchi-Hansen instantons. For that, we'll consider Young-Mills prototype, a SU2 prototype of GCD. And this is one of the simplest solutions on Iguchi-Hansen space-time. known as a standard embedding. So there is a class of actually those hybrid instantons, but this is the simplest one and the most relevant one for our case. So as you can see, A here is the SU2 gauge field, and omega is the spin connection, the gravitational spin connection, and they are related with this relation, with a very simple relation. And this is a solution of the combined Young-Mills gravity equations. What is interesting is that if you compute the action of this solution, of course, the gravitational part is again 0, but the Young-Mills part gives you, in this particular case, this value over here. So now it looks like that we have n equals 3 instanton here, type of instanton, but again, instead of 8 pi squared over g squared, we have a factor 4 pi squared over g squared. And this is the result because we basically halved the integration space. Okay. All right, so you can compute the various topological characteristics of this manifold, of the solutions. First is, of course, Pontryagin index in this particular case. And this is a Pontryagin index, as I said, with set normalization is equal to 3. You can compute also the fermion index. And this, of course, depends on the representation of fermions. And if I take a dr-dimensional irreducible representation of SU2, here is a formula for the index of Dirac operator. What you can see from this, if I take, for example, the fermions being singlet under the SU2, that means they don't couple to the gauge field. The index of the Dirac operator is 0. Okay, so but if they are charged under the SU2, then fundamental fermions gives the exactly index theorem is equal to 1. Okay, like for the BPST instantons. So what you expect then is that beside the term, the typical term which is induced by the usual instantons, say BPST instantons, you will have the similar type of operator, but with a different prefactor. Okay, so there will be a additional contribution to each of these instantons in the effective action. All right, so now in the effective action, we also have 2 different theta terms, which are not reducible because of the presence of the extra instantons and extra instanton configurations. And you can also argue that the effective theta angle, which enters the calculations of, for example, neutron electric dipole moment, is set in combination of the gravitational theta term and the QCD theta term. So the question then is, how does this affect the original solution of the Pechet-Quinn one axion solution? For that, you can go and do the standard instanton calculus in the dilute gas approximation with all the problems it has, but at least qualitatively it gives you this result over here. So the first is the usual one instanton anti-instanton contribution, and the second one here is the contribution from these gravitational instantons. And as a result, we have now 2 cosine terms, and the important thing is the relative size of these cosine terms, obviously. And since this second contribution is also dominated by the large-scale instantons, not small-scale instantons, we can find that this contribution, the second instanton contribution, is quite sizable compared to the usual QCD contribution. And what does it mean is that this completely compromises the standard solution of the Pechet-Quinn. And so one axion solution, if we believe to these contributions, are not valid anymore. Okay. All right, so what you can do, you just can follow Pechet-Quinn, the simplest thing. And you stick with the Pechet-Quinn solution, then you can just extend the Pechet-Quinn symmetry by simply postulating 2 Pechet-Quinn U1s, which are spontaneously broken. And in that case, of course, you predict the existence of the two axions. One is what we call the companion axion, in order to fully resolve the strong CP problem under the influence of the gravitational instantons. Okay, so this would be the effective potential for the instantons under these conditions. Okay, there is one caveat, of course, with this. We can assume that there is a contribution from neutrino sector, obviously, and there, if we assume that the neutrinos are Dirac particles, and one of those species are massless, you can use that kind of massless quark interpretation solution in this case as well, without introducing extra axiom in principle. But if all neutrinos are massive, then you need the second axiom. So that's a key point. All right. So now you can, if you believe to that, then you can go and look at the phenomenology. And we wrote two papers, which just touching upon the more rich phenomenology of these axions. First of all, you can distinguish, at least qualitatively, two different cases, where the first one where the breaking scales or decay constant for these two axions has a hierarchical, they are hierarchical. And another one where they are of the same order of magnitude. And qualitatively, the situation are different here. One is you have more or less hierarchically separated masses. And in another case, you have almost degenerate masses for the two axions. Another thing is that, of course, there is a lot of effects, associated with another case. One could be the axion oscillation effects, which one can study more carefully. But one of the things is that so you always have heaviest axion is a kind of standard PCD axion in any case, and the second axion is usually lighter under the normal circumstances. So this is a typical. So of course you can go in with the model building here, but here I'm talking about more generically, just assuming certain anomaly numbers here, just for illustrative purposes. And so here is a typical situation where we have the QCD axion over here, and then by the dotted line we have another companion axion, which is predicted in this theory. So the interesting thing about this, I'll show you a few figures, is that you can by detecting one of them, you can kill the whole theory in principle. Okay. Or you can detect or constrain the whole theory as well. So here is the plots on the constraints on these axions. Now you can see that this looks like a little bit different from the usual axion plots, because we have now a multidimensional space. So this is basically written in as a decay constant of one axion, the kind of QCD-like axion, and another companion axion, the ratio. And you can see that there are standard limits from the star pooling, what Alessandro was talking about. ADMX limits are extended because you have the extended mass spectrum of another axion, and also this black hole superradiance limits are extended. So if you kill one axion in one limit, you kill another one as well, because they are correlated. So interesting thing is that, on the other hand, that you have a chance to detect both axions, in fact, in one or different experiments. Okay, we have a sensitivity to this, and this plot illustrates this, that you can, in principle, detect, for example, in this range of parameter, two axions at I axion. So these are the kind of smoking guns of this theory. So Now, of course, another thing is the cosmological implications of these axions, the companion axions. Of course, now both axions can contribute into the dark matter. And of course, there's the whole dynamics related whether these axions produce before inflation, after inflation, both before inflation, both after inflation, and there are various possibilities, obviously. So again, we did not investigate all of them, but there is clearly some correlations between where you can have this band, for example, relative, which is related with the relative amplitude of these two axion fields, and potential constraints related with that. So one more interesting thing about this axion also in generic model is that typically with the generic axion models we have so-called axion domain wall problems. And the typical solution is that you just violate explicitly the Pecha-Equine symmetry, just set on levels, or not to disturb the Pecha-Equine solution, but on the other hand to make the walls disappear. Here, in general, because we have two cosines and the anomaly numbers are not necessarily aligned, the Pecha-Equine symmetry, the residual discrete symmetry after the breaking Pecha-Equine symmetry are actually strongly broken, in generic case. So you don't expect actually most of the domain walls to be formed unless the axions are in a very small mass range. In that case, the axion domain walls will quickly collapse, and there are a few effects out of it. Is the formation of primordial black holes, and you can roughly estimate the masses of these black holes for order of 100 solar mass, and you can also estimate what is the abundance of these black holes, but this estimate is highly non-trivial because it's just an analytical one with a lot of uncertainties there. So this is about primordial black holes, which are related with the dynamics of the axion domain walls. And another interesting feature of this, again, is related to the production of the gravitational waves. Again, very rough estimate tells you that this is in a nanohertz scale. And I think you all heard about some tantalizing evidence for the existence of the stochastic background of gravitational waves. All right, so this is all what I wanted to say. So just concluding, the contrary to the widespread belief, the non-perturbable quantum gravity effect may have significant phenomenological implications because they are changing vacuum structure of the theory and the standard model in particular. And the interesting thing which we identified is this hybrid gauge Gucci-Hansen instantons, which gives the spin structure by itself, or the existence of fermions in the world, gives the electric charge condensation immediately. Okay. There is an extra unexplored sources of CP violation within the standard model, as I believe, and of course there is a potential implications for the cosmology. In particular, we discussed the companion axion solution because of this extra contribution. The standard solution, I believe, is compromised completely. So you need at least the second axion. And there is a very rich phenomenology associated with this companion axion model, which we just touch upon in these other works, the initial works. The cosmology includes the dark matter, gravitational wave signals, and also LIGO size black hole predictions. Thank you.
So thank you for this nice talk, and now it's time for questions.
I have a comment, not question. Just maybe some people have. Okay. So Archil, I have a comment. So essentially, as you know, these instantons in QCD instantons and Toft operator, of course, is irrelevant for CP because it is a correct operator only for very large temperature or for electroweak for small coupling constant.
Yeah.
When you have actually a coupling constant, QCD coupling constant, everything is completely different. It is not Toft resolution with the operator, but Witten-Veneziana resolution.
Yeah.
So in order to see if you have anything to say about new CP, you have to compute so-called topological susceptibility extra contribution, and you have to convince us that there is an anomalous contribution to the topological susceptibility, which is expressed in conventional way in terms of the chiral condensate, and after that you have to actually see what's happening with the behavior of the chiral condensate as a function of additional theta, and after that just to say what is a new contribution to CPAs. But the Toft part definitely can be applied only for very, very high temperature. You can say the same about electroweak. There is actually instantons in electroweak field theory, and we absolutely ignore that because it is extremely small. And the same is here. It is a small when instanton contribution is calculated the way how you calculate it. It is only for very, very small weak coupling regime, not for the strong coupling.
Oh, absolutely. Yeah, I agree. I mean, so it's of course what is used in this calculation is the dilute gas instanton approximation, which of course for the QCD is invalid. No, not incorrect. Invalid. Invalid, of course, because in the QCD, of course, it's all defined by the more infrared physics rather than this large scale instantons or relatively large scale instantons. Yeah, I agree with that. But the key thing is that the relative contribution, I think, will remain. And with the topological
Constraint that you have to compute additional contribution.
Yes.
Topological susceptibility.
The topological susceptibility, I believe that yes, okay, I agree. I think it's very hard to compute everything was related with the gravity, but I believe that there is a mixed topological susceptibility of GG dual and RR dual. Okay.
Everything is possible. I don't know, but nevertheless, at the moment, I'm not convinced because of the simple reason. Because you have to compute strongly coupling you have to compute topological susceptibility.
I think okay. Let me go to the following thing. So okay, so if I treat the gravity as just on the Eguchi-Hansen background, so let me abstract from the quantum correction to that, then I think the topological susceptibility can be computed the same way as in QCD. It's just a different type of instanton which contributes.
We do not compute topological susceptibility.
Yeah, I know, but
we compute using anomalous commutation relation.
That's right. Yes, one of the contributions are instanton contribution. Maybe the
is expressed in terms of the chiral condensate, and we compute chiral condensate using the latest field theory, not from instanton.
Okay, I don't know how to do this in lattice gate theory, but the key thing is that one of the contribution, maybe not dominant, is because of the instantons, obviously.
Thanks for the talk. So I'm a bit confused why the magnitude of these two terms are almost the same.
Yeah,
I guess I would have expected if I take the limit G Newton goes to 0 that the gravitational instantons would decouple, but I didn't see but G Newton doesn't seem to be playing a role here. So
yeah, I think this is so the point is that the gravitational part of the action is 0 actually, and for this configuration according to this positive action, not conjecture. It's actually a theorem to prove that. What contributes is only the Young-Mills speed in here. Now, let me show more carefully. There is. Oh no. Yeah, so in the flat space-time limit, you're absolutely right, because the size of the both instantons are governed by this, what is this? Yeah, by this parameter A. Sorry. By this parameter A, which is, so if you take a flat space-time limit, this reduces to 0. So that's why I'm talking about that this is a large-scale effect, not a small-scale effect. Okay, for large-scale instantons, the effect is there. Okay, so the reduction to the flat space-time, as you're talking the G going to 0, of course, it decouples gravity completely, and then you're back to the usual contribution.
Thanks.
More questions?
Yeah, thanks for the. Engaged theories, this should be satisfied necessarily.
In Young-Mill theories, the action is positive, definitely, right?
No, not the action. Okay, you had one of the first slides, you had a statement that the vacuum had to be interfered because of cluster decomposition. Or
I'm not quite following the question. Sorry, can you repeat it?
please go to the first slide.
First slide.
First slides, yeah. No, even before, I think. Yeah.
Okay.
Here, I think, yes. So this term is mandatory to preserve causality, and you have cluster decomposition. So this is what confuses me, because is there a theorem which states that cluster decomposition should be satisfied
Yes.
in non-abelian theory? So what is this theorem? Because I thought it's
Well, the existence of theta term, yes, you're right. I mean, it follows from the cluster decomposition. You have to choose the theta vacuum. No.
yes, but why should cluster decomposition be mandatory in non-abelian field theory? So this is the question. Because you claim that this is a mandatory thing following from causality, but I don't see it.
Yeah, for Young-Mill theory, the existence of theta term in that's a standard argument that you have to take in Young-Mill theory theta vacuum to satisfy the cluster properties of the theory, right?
Yeah, but
Non-abelian theory.
Asking why this cluster property has to be satisfied in the first place. Okay. And another question. So
Yeah.
could you please maybe comment more? How do you derive this? How does this charge quantization arises from?
Yeah. Well, okay. So
Maybe
this is okay. Maybe I have a backup slide. I can quickly show you. So in essence, as I said, this is related to the definition of it. So you should be able on the curved manifold to define the spinors. That's one of the conditions. And these solutions has this horizon, which in the near horizon limit, it's a flat space time with a singularity. Okay, so if you go around the singularity, you will quantum mechanically, of course, classically you don't have anything, but when you go around by the fermion classically, you pick up the phase, okay, which should disappear, and that's where the quantization comes from. This is a similar thing as happens for the monopoles.
So do you have like effective magnetic monopole here, or?
Well, it's not effective magnetic monopole. It's a electrically charged Deguchi-Hanson spacetime.
Okay,
it's acts
so
like
something different from the monopole.
Yeah.
Okay, thank you.
Okay.
On the previous slide, you had these expectations for black holes and gravitational waves from the domain wall collapse. Couldn't the collapse mainly generate the Goldstone boson, I mean the axions themselves?
Yeah, the radiation of axions.
Most of the
Yeah.
energy will go into the axions.
Yeah, okay. So the assumption here is that most of it
Yeah.
goes to the gravitational waves, but you're right.
How do you get bands? How do you get the normalization?
Yeah, the assumption here is that most of the energy is released into the gravitational waves rather than axions.
I see, but
Yeah.
there is no criterion for deciding.
No. Yeah.
Thanks.
Okay, more questions? No, I don't see any question from remote. So we thank Archil again.
Thank you.